Yes, good evening once again, dear students. Today is the 7th February 2025 with your expert engineer Sachid Hood. Today I want to share with you how to model geometric distribution using binomial distribution. So we know for geometric distribution, our main target is to obtain the first success regardless of the number of trials you take or you get. But what if we are required to determine the second success, having obtained the first? Have you ever wondered how to do it? I got a simple formula for you. Check. The problem comes. Raj has a chance of 0.2 to shoot at a monkey on any attempt independently of all other attempts. Determine the probability that he shoots at the monkey for the first time in Roman 1 less than 4 attempts. 1. To do this problem, to solve the problem, we need success probability, which we know is 0.2. And we have the failure probability, which is Q, and is 1 minus P. I have my 0.8. Of course, we know, and we have to remember that what they want is probability of x less than 4, which is the same as probability of x less or equal to 3, because we have 1, we have 2, we have 3, okay? Those are the numbers less than 4. We can't write 0 because we are trying to obtain a success, okay? The first time. That's why you're seeing me putting probability of x less or equal to 3, which is 1 minus q power 3. And the answer comes as 0.488. You press your the calc very well, use brackets and cube very well, you have the answer there. Then they're saying here, Roman 2, above 3, but less than or equal to 7 attempts. So that is the mathematical language I've used here to simplify that. This is simply q power 3 minus q power 7. How does it come? Look, probability of x, mean 3 less than x less or equal to 7 is probability of x less or equal to 7. When we say less or equal to 7, we are meaning 1, 2, 3, 4, 5, 6, 7. But remember, 3 is not inclusive. The symbol here excludes 3. That's why I had to subtract probability of x less or equal to 3. And I know it is 1 minus q power 7 minus open brackets 1 minus q power 3. When I simplify, it becomes q power 3 minus q power 7, which will be like that. And therefore, there I'm good. Now, there's part B of the question. They're asking me that find the probability that Raj shoots at the monkey for the second time on or before his 6th attempt. So this is purely modeling geo using binomial distribution. If we let k to be the number of times we shoot at the monkey and n be the number of trials or attempts, I made for you the formula. I've not yet given it a name, but the formula is probability of y is equal to n, comma k is equal to n minus 1 combination k minus 1 times probability of success power k, probability of failure power n minus k. That's my formula. So I've not yet given it a name. Use it. Use it for humanity. So let's see on a second attempt, because I cannot consider the first attempt. Remember, one attempt gives one success, and yet the question wants the second success. So I have to begin from attempt number to n equals 2. This 2 you see here is the k here, the number of times I'm shooting at, and I'm shooting at it, the monkey, I mean, the second what? The second time. So k is 2. That's why this is going to be, if I substitute this 2 minus 1, which is 1 combination, k minus 1, k is 2, so it is 2 minus 1, which is also 1. The success will be power 2, because those are 2 successes. I'm shooting at the monkey 2 times. That means there's no failure, zero failure. I'll get the answer. Now on the third attempt, it will be 2 combination 1 successes twice, 1 failure. I will have that because they're independent events. Then on the fourth attempt, of course, we have a 3 combination 1, 0.2 power 2, and 0.8 power 2. If you observe very well, the powers add up, like 2 plus 1 adds up to the number here, number of trials. And even here, 2 plus 2, this is 4. This is 2 plus 1 is 3. 2 plus 2, 4. We look at this, 2 plus 3, 5. Then, of course, they said on or before 6th attempt. So I have to include the 6th attempt. Get probabilities, all, and I add. I have my answer as 0.3446. Thank you for watching. Have a good night.